Okay, in this video we're going to take a look at graphs of logarithms. There are two kinds of ways that you can approach this if you need to actually plot points, which we need to start with for now. So let's look at log base 2 of x. And our typical approach when we don't know what a graph looks like would be to plug in some values of x and get values of y. So let's start that way. So I need to plug in values of x. A lot of values of x I won't be able to figure out what they are for log base 2. So let's plug in values of x that we can figure out. So remember our property log base a of a to the b equals b. If I can get the bases to match, then I can take the logarithm by hand and I won't need a calculator. So in order to get bases that match, I need powers of 2. So I need things like 8, 4, 2. I could also do 16, 32, 64, but those are pretty big. This will give us a good graph. So when I plug those in, I'm going to get log base 2 of 8 for this one. And I use this property over here to rewrite that as log base 2 of 2 cubed because I want the bases to match. And the logarithm says what's the exponent? The exponent is 3. So I get the 0.83. And then doing the same as we move down the list, log base 2 of 4 would be 2 squared, and that would be 2. And log base 2 of 2, anytime you take a base of its, or a log of itself, the exponent's implied to be a 1, so that would just be 1. And then we also talked about 1. Remember that any log of 1 is going to be equal to 0, or if you don't remember that, we can rewrite 1 as 2 to the 0, and the logarithm is the exponent, so that's equal to 0. Okay, so this gives us a pretty good start. Let's go ahead and graph this and see what we're at. All right, so we need to go out to 8. Okay, 2, 4, 6, 8, and 3. 4 and 2. 2, 1, and 1, 0. Alright, so 1, 0, 2, 1, 4, 2, 8, 3. If we kept going, think about what you would have. Every time the logarithm is the exponent. So if I did 16, that would be exponent 4. 32 would be exponent 5, 64 would be exponent 6, and so on. So these would go up very slowly because our x values would get really, really big. But we would kind of have this sort of shape, and it would keep getting bigger just very slowly. It would be going more to the right than up. All right, so that's our first part. Kind of like the exponential function. It kind of looks like a parabola, but it's going to be steeper. All right, now, the graph doesn't just cut off here. That's just as far as we went. There are more values, but remember when we talked about the definition of a logarithm, the base and the number inside of the logarithm have to be positive. We can't have 0 or negative. So the part of the graph that we're missing has got to be these numbers between 0 and 1. So that means that we need to put fractions in. And usually fractions are kind of tough to deal with, but what kind of fractions could we deal with? If you remember, with exponents and looking at the simplifications, if we do the reciprocals of these, we should be able to take the logarithm. So let's try 1/2, 1/4, and 1/8. Okay, so log base 2 of 1/2, I want to rewrite that with the same base. So reciprocal means negative exponent. So that's going to be the same as 2 to the negative 1, and the answer is negative 1. Similarly, for 1/4, we need a reciprocal. So that's going to be negative. And then how do I get from 2 to 4? To get from 2 to 4, I square it. So negative 2 tells me to flip it and square it. So flip it and square it, I get 1/4. That means those are the same. And the logarithm, when the base is matched, the logarithm says what's the exponent? The exponent is negative 2. And our last one, this should hopefully be making sense by now. All right, if I want to rewrite 1/8, I need to flip it and cube it. Flip it and cube it, so that gives me an answer of -3. Okay, and again, we could keep going 1/16, 1/32, 1/64, but we're not going to be able to graph that anyway. So let's try and see what we have. So at 1/2, we've got -1. At 1/4, we've got -2. At 1/8, we've got -3. If we kept going, we'd have 1/16, -4, 1/32, -5, and so on. So the x values would keep getting closer and closer to 0 because we keep taking half, but we never actually reach 0 because 0 is undefined. And as we did that, the y values keep going more and more negative. So we're going to go like this, and we're going to have an asymptote at 0 because we're going to get closer and closer to 0, but we can never actually reach it. Okay, so this is our graph of log base 2. Let me write that on there. That's log base 2. Now, this should look kind of familiar to you, and we've been talking about how logarithms and exponentials are going to be inverses. Well, they are inverses. We're going to see that they're inverses next week. So the other way that we could tackle this, we can do this, and really once you know what it looks like, you really could just plot these 3 points like we did for the exponential. You can really just use 3 points to figure out where the graph is. So that's another option as well, is just simplify this. So this is one way to do it, kind of brute force, plug in the x values, get the y values. The other way to do this is to remember that this is inverses. This is an inverse function with 2 to the x. And we've talked about inverses. Remember, graphs and their inverses, we swap the x's and y's. So when we looked at 2 to the x, let me put this in another color. Okay, so remember that we plugged in a bunch of values for x, like -3, -2, -1, 0, 1, 2, 3. This should be in your notes. And when we put that in the exponent, we got 1/8, 1/4, 1/2, 1, 2, 4, and 8. Uh-oh. Okay. I don't know if you guys are seeing this pop up. I apologize for that. Oh my gosh. Sorry about that. It's a new computer, and I just used the free antivirus that I grabbed. Sorry about that. Okay, so back to this. This was our table for 2 to the x that we used to graph that and kind of get an idea of what happens with exponentials. If you look at this table over here, look at our x values and look at our y values. I probably should have gone the other direction so you could see. This table is like upside down from this one. But look at the y values, 8, 4, 2, 1, 1/2, 1/4, 1/8. And then look at the y values here, and again, they're going to be flip-flopped. Okay? -3, -2, -1, 0, 1, 2, 3. Look at that. It's exactly the same as the y values. The x and y values are reversed. So that's another way that you could do this, is if you want to do log base 2 of x, you could get the values for 2 to the x, which is a little bit easier to figure out, and then flip-flop the x and y values. You could also graph 2 to the x. Okay, 2 to the x looks like this. And remember that inverses reflect across the diagonal. So look at that. You could also get a graph by reflecting across the diagonal. That's probably the least straightforward way to go because it's a little bit hard. Remember that was a little bit tough to try to graph that across the diagonal. Okay, so this is 2 ways to do it. One is to plug in values that you can find a log for. And the second is to use the inverse function and then switch the x and y values. So let's try another one. Let's try y equals log base 3 of x. Alright, so let's just do a few values plugging in x, and let's just do a few values of 3 to the x, and then we can compare them. Okay, so if I'm doing log base 3 of x, what type of numbers can I plug in? I can plug in 3, 9, 27, 81. I can plug in powers of 3, right? So these get pretty big pretty fast. 9 and 3 are really the only ones that we can do. We can always take log of 1. That's an easy one. And then I can do the reciprocals, 1/3 and 1/9. Okay, so if I can do 3 and 9, I can do 1/3 and 1/9. All right, so when I do these, maybe we're getting a little bit faster at them now. I want to get the bases to match, so I'd write 9 as 3 squared. Bases match, the answer is 2. Log base 3 of 3, the exponent is implied to be a 1. Log base 3 of 1, remember any log of 1 is 0, or you can rewrite this as 3 to the 0. Log base 3 of 1/3. 1/3 is the same as 3 to the negative 1. And log base 3 of 1/9. Okay, 1/9 is the same as 3 to the negative 2. I have to flip it and square it. Okay, so that's our table if we were to go at it directly. Our other option would be to do a table for 3 to the x. And this time I'm going to keep the numbers in the same order. So let's say I do 2, 1, 0, negative 1, negative 2. Those would be pretty easy ones to plug in. So when I plug those in, I'm going to get 3 squared is 9. 3 to the 1 is 3. 3 to the 0, remember anything to the 0 is 1. 3 to the negative 1, that means reciprocal. And 3 to the negative 2, I flip it and square it. Okay, now these are the values for 3 to the x. So if I want y equals log base 3 of x, I'm going to reverse all of those. Remember, we did that with the inverse. Switch the x's and y's. So I'm going to get 9, 3, 1, 1/3, 1/9. And then I'm going to get the x values become the y values. 2, 1, 0, negative 1, negative 2. Okay, so this would be one way to do it. Plug in the values and get the answer. This would be the other way to do it. Use the inverse. See, the bases match. Use the inverses and then switch the x's and y's. The table that I get here, whoops, pen went a little crazy on me there. Okay, the table that I get here is the same table that I get here. It's a little bit more spread out, but look, we get the same values. 9, 3, 1, 1/3, 1/9, 2, 1, 0, 1, negative 1, negative 2. Okay, let's get rid of that. I zoomed in somehow and I'm not sure how. Okay, we'll just kind of go with it. Alright, so let's move this over here and let's go ahead and graph Alright, so we've got 1, 0. We've got 3, 1, we've got 9, 9, 2. Okay, so there's that part that's going up and out. And then the fractions, 1/3 we get negative 1, 1/9 we get negative 2, 1/27 we get negative 3, and so on. Again, we're going to get closer and closer to the y-axis, but we're never actually going to reach it. Okay, and again, the y-axis is an asymptote. Alright, so if you look back at your notes from y equals 2 to the x, you'll see that they're very similar. They both cross at 0, 1, they both go up to the right, and they both go down to the left.